welcome to Luohan Webinar. I'm your host, Sang Choi. So today we are very happy and honored to have the Professor Alessandro Acquisti. Alessandro is a trustees professor of the Information Technology and Public Policy at Carnegie Mellon University's Heinz College, and the co-director of the CMU Center for Behavioral Decision Research. He's a fellow of the Ponemon Institute and a member of Carnegie Mellon SciLab and the SciLab Usability, Privacy, and Security Lab. Alessandro has been the recipient of the PET Award for Outstanding Research in Privacy-Enhancing Technologies, the IBM Best Academic Privacy Faculty Award, the Heinz College's School of Information Teaching Excellence Award, and various Best Paper Awards. So Alessandro's research investigates economics and behavioral economics of privacy and privacy in online social networks. His studies have been published in leading journals across diverse disciplines, such as Proceedings of the National Academy of Science, Journal of Consumer Research, Marketing Science, Information System Research, and many others. So today he's going to talk about his paper, The Policy Impact, Statistical Uncertainty, and Privacy. So we're going to have 1 hour, and I think that the audience can ask the question in the middle, or do you prefer to have a separate?
Please, absolutely.
Okay, yes, so the floor is yours. Yeah, please.
Well, thank you so much. Thank you, Sangu. And thank you very much for the invitation, and to all of you for being here. I look forward to discussing this work with you today. I will spend most of my time focusing on the study, which is describing on this slide. It's a study we published just a few months ago with collaborators also from CMU. I'm lucky that Ryan Steed, the first author, is also on the webinar today. And this is a study about policy impact of statistical uncertainty and privacy. Essentially, it's a study about differential privacy in the census. But before I dive into the study, I would enjoy the opportunity of framing this study in the context of the research that I and others are trying to do at the moment, at the overlaps of economics, data, and privacy. It is very important to me to contextualize this study, because it's really part of a research agenda that attempts to tackle what I personally believe are understudied research questions. And therefore, my talk will be what I call the glass hour sort of talk, meaning that I will start very broad, couple of slides contextualizing. Then I'll go very narrow, and this is where we will be spending most of the time discussing one particular study, the one on policy uncertainty and the impact on policy. And then near the end, at the end, in fact, of my talk, I will open up again to the bigger picture, if we still have time. Okay, so this is the plan. So the big picture is the following. I and many others have been working for a while on the economics of privacy, the economics of personal data. I was lucky to work with Curtis, Taylor, Leah Wagman, and published in 2016 in JEL a review of the economics of privacy. Since 2016, this field has further expanded. In fact, one could even say almost exploded. There are more and more studies being done using economic tools to understand the impact of privacy regulation, the effect of behavioral targeted advertising on effectiveness, and so on and so forth. So much so that my colleague Catherine Tucker and Avi Goldfarb hosted just last year in 2022 and at the NBER 2 different events on economics of privacy. One was a workshop on economics of privacy. The second was a tutorial with PhD students on economics of privacy. And as part of the second event, the tutorial, they asked some of us to write some chapters about the state of the field. And my chapter focus, and here is the title, The Economics of Privacy at the Crossroads, focus on what I personally, this is my very personal opinion. Certainly it's not NBR opinion or Catherine's opinion or Avi's opinion. But my chapter focuses on my personal opinion, what is the state of this field of research. The research, this field has grown dramatically, and this is great. There are many interesting contribution, but in some sense, it has crystallized over an opposition between a future with more data and a future with more privacy. And they are seen as antithetical to each other. So either we have more privacy, which implies less privacy, either we have more data, which implies less privacy regulation, fewer privacy protections, or in fact, we have more regulation, more GDPR, more CCPA, more privacy bills, federal privacy bills, more regulation in China, in Asia, in Africa, and so on and so forth, which gives us more privacy. And if we want more data, and therefore less regulation and protection, we get all these economic benefits of more data. More efficiency in transactions, more technological innovation, et cetera, et cetera, et cetera. If we instead have a regulation, well, we may protect the privacy. In so doing, we may protect important but hard to quantify values such as autonomy, dignity, and freedom. But we also have a loss of economic costs, because much of the literature in this field is focused on the cost of protection, the cost of regulation. You just look at what has been happening with the GDPR, and we were just chatting about this a few minutes ago before the webinar started, and you see plenty of research highlighting the cost caused by privacy regulation on a number of economic variables versus the benefits that absence of regulation and more data exchanges can create. Now, no problem with research questions focusing on the cost of regulation and the benefits of data transactions. However, what I find slightly problematic is that we have, I believe, and this is my personal opinion, I believe we have understudied very important research questions, such as how much do we really know about the downstream negative impact of the absence of privacy? So if we give up on autonomy, dignity, and freedom because we don't have privacy protections, what are the downstream costs? How do they affect society? That's an understudied area. To the extent that value is created by the collection and analysis of personal data, and I believe that value is created through that, what do we know about the allocation of that value? In other words, when, for instance, behavioral advertising relies on the collection of vast amounts of consumer data to target ads to consumers. What do we know about the benefits that the different stakeholders, the advertisers, the consumers, the intermediaries benefit from this vast architecture of data collection? And finally, what do we know about the inherent assumption, the implicit assumption of a tension between data and privacy? Either we have more data or we have more privacy. Can, in fact, have them both. And this is really the focus of the paper, my study today, because in the last 20 years, 20, 30 years, statisticians, computer scientists, cryptographers have produced a number of tools which may allow us to protect privacy while still extracting value from data. And those tools for a long time have been somewhat ignored in the economic literature. Finally, it seems that things have been changing. In the last perhaps maybe 3 to 5 years, finally, a number of scholars, and I will mention their names later, have started focusing on analyzing the impact of these tools. And this is really what the study I'm going to present today is about. We study one particular tool called differential privacy, and we study its impact in one particular application, which is the census use or future use of differential privacy in its own statistics. And like I said, this is joint work with Ryan, who is connected today, Terence Liu, and Stephen Wood. So what is differential privacy? I'd like to distinguish between privacy-enhancing technologies at large and what I call privacy-preserving analytics specifically. Privacy-enhancing technologies are a number of tools which, indeed, have been developed over many, many years to protect personal information privacy while individuals engage in digital transactions. They can work in many different ways: data anonymization, de-identification, obfuscation, and so on and so forth. And when I started working in this field 20 years ago, as I was finishing my PhD, while back then those tools were only known by a few experts and only used by a small number of people, think about Freedom Network, which perhaps had only maybe 20, 30,000 users at the time, and which was an anonymous browsing tool, essentially, which existed over 20 years ago. Nowadays, those tools have become very, very common. And I'm sure that many of you use at least one, perhaps two, perhaps all of these three tools. Signal, which is a messaging platform with built-in privacy and security property. PGP, Pretty Good Privacy, which is a suite of encryption tools for protecting data and emails and make it easy, or at least much easier than before, for lay users to encrypt their communications and their data, or VPNs, which also are privacy tools, because they allow a user browsing the internet to do so without necessarily leaking their browsing behaviors to other entities, such as the ISP, maybe some government observer, maybe some hostile hacker, and so on and so forth. So these are examples of privacy enhancing technologies. One particular type of privacy enhancing technologies is what a number of us have started referring to and calling privacy preserving analytics. So it's a particular type of technology, or rather set of technologies and set of tools, protocols, and frameworks, which is intended to protect individual data while still allowing a beneficial usage of data. For instance, while still allowing analysis to be done on data. And over the years, many such approaches have been proposed. K-anonymity used to be one of the most well-known. My friend Latanya Sweeney was one of the people behind K-anonymity, and K-anonymity was born out of the recognition that re-identification attacks are realistic and they're dangerous. Latanya became famous as if she was finishing her graduate studies by showing that you could take medical discharge data in the state of Massachusetts. She was doing her PhD at MIT at the time. Medical discharge data from Massachusetts hospitals, which is anonymized or at least de-identified, but contains information such as the gender, the date of birth, and the zip code where a person being discharged by the hospital lives. You could combine that to electoral voting registration list, which have names of people and also personal information. And you could then end up connecting the two and end up re-identifying and give a name to people in the medical discharge data sets. Essentially, she demonstrated that individual pieces of information that in and of themselves are not uniquely identifying anyone. The gender doesn't uniquely identify anyone. Zip code does not uniquely identify anyone. Date of birth does not uniquely identify anyone. The three of them combined could uniquely identify people, according to her estimate, a significant proportion of the US population. In response to this, she proposed K-anonymity, which was a framework for databases containing sensitive information, such as medical hospital discharge data, to be publicly released only if certain properties are met, such as each piece of sensitive information matching at least K other individuals, where K could be a large number, such as 1,000 different other individuals. David Chaum, a very well-known Dutch-American cryptographer, proposed homomorphic encryption as a way to anonymize voting, to anonymize payments online. Homomorphic encryption essentially is a cryptographic tool which leverages some interesting properties of some very specific encryption algorithms, such as, for instance, El-Gamal, and allows essentially to do computation in the encrypted space, which translate then to corresponding matching computation in the unencrypted space. What does it mean in practical terms? It means that you can take pieces of data which may be sensitive and therefore may not be shared publicly. You can encrypt them, and then the operations can be done on the encrypted data, so that the operations are done without revealing the underlying private information. And this operation in encrypted data can then be transfer to results for the unencrypted data. For instance, you can do auctions using these tools. You can do payments. You can do voting, and so on and so forth. Federated learning, another tool. In fact, Google was planning to use some kind of form, not exactly federated learning, but a kind of form of federated learning in some of his proposed plans for a post third-party cookies world. As you may know, there has been a movement against tracking, cross-device tracking with third-party cookies, and Google has been at the forefront of trying to look for different solutions to allow behavior advertising to survive. In a world without third-party cookies. They propose federated learning of cohorts, flock. Eventually, they abandoned that. Now they are focusing on different approach topics. But the point is that there has been research on these kind of multi-party computation approaches, distributed computation approaches, which may allow analysis of data while protecting privacy. And finally, differential privacy. And differential privacy is going to be the focus of the rest of my discussion. Why? Because differential privacy in the last few years has become increasingly popular, first among computer scientists and statisticians, and then, as I was hinting at a few minutes ago, also among economists. And a number of well-known economists have actually started analyzing differential privacy. So we finally have this convergence, right, between computer scientists and economists and social scientists, which I find extremely exciting. Differential privacy, in essence, works by adding noise to data. Under differential privacy, it can be guaranteed that the outcome of any data analysis is nearly equally likely whether any specific individual record is or is not included in the dataset. And this is great in that it allows the application of differential privacy, allows to obscure whether a particular data record, such as, for instance, a particular individual or a small group of individuals, are in fact in a data set or not, while we can still preserve, to some extent, statistical utility, in that we can still run statistics which should produce results which are comparable to the results that would be obtained with the to the ground truth of the database to which no noise has been added. And with differential privacy, we can quantify the level of disclosure risk, even when we may not know ex ante which algorithms or which other databases an attacker may use. Imagine the re-identification attacks that I was mentioning earlier. Imagine Latanya Sweeney's work, combining two data sets to re-identify individuals in the sensitive data set. One of the problems which were well known with solutions such as k-anonymity is that their strength in terms of protecting individual data relied on which other external databases an attacker may get their hands upon. And because it is not possible to predict ex ante which external datasets an attacker could use, then k-anonymity could in fact suffer from that type of attack. Less so with differential privacy. So differential privacy for a number of years was mainly or mostly discussed by computer scientists and cryptographers and statisticians, but not by organizations in the public or in the private sector. And then in the last approximately 10 years or so, both private sector organizations and public sector organizations started thinking seriously about differential privacy. And I believe that the US Census is probably one of the organizations that has been at the forefront of the movement to use differential privacy for practical purposes. And this is probably due in good part to the work of a well-known scholar, John Hubbard. At the census, while he was at the census for a number of years, he started this discussion of applying differential privacy to census data. Because of statistical property of the framework, differential privacy, and I'm quoting the US Census here, allows the Bureau to limit the disclosure risk of published data. If the output of an analysis is essentially the same, regardless of whether a given individual is in the dataset, then the person's confidential information is protected. And there are numerous ways to implement differential privacy. This means that differential privacy is a characteristic of an algorithm or a process, not a specific algorithm. And this is important for census, right? Because census, as one of the goals of census is, of course, to allow other entities, other agencies, and individuals and scholars to do analysis with census data. We rely on census data for many, many important pieces of research, as well as for many important decisions that the rest of the government makes. In fact, I will focus on one of those shortly. But at the same time, the census has an obligation of confidentiality towards census respondents. So differential privacy seems to be able, perhaps more so than the many other disclosure avoidance mechanisms that the census has been using over decades, to match these apparently seemingly conflicting goals. Allow research on census data, allow the use of census data while protecting confidentiality. But as economists, we know that there is never a free lunch, right? So adding noise to data does create inherently trade-offs. And this is where much of the attention has been focusing, not just in the public discourse, in the media, in a number of articles, kind of making light fun of the attempt of the census to use differential privacy by pointing out that now, because of this noise adding, it seems that people in a certain zip code live underwater. But also, this is just the public-facing version of a very important debate that has been happening among scholars and also among politicians. So we have demographers publishing research on the potential detrimental effect that the application of differential privacy could have on very important calculations and very important analysis that demographers are used to do with census data. And where politicians, first Democratic politicians, then Republicans, also getting worried and protesting the application of differential privacy for issues related to redistricting, which for anyone who lives in the United States, we know to be a very, very contentious issue in our elections. And then also civil rights groups based on the Voting Rights Act and the problematic aspects that the application of differential privacy to census data may perhaps entail. So there is this debate, right? And it's a useful debate. It is an important debate, and it is a legitimate debate. What, however, in our study point out is that much of this debate focuses on the noise caused by differential privacy itself. So there may be a data point or in fact a statistics that it is assumed to be correct, it is assumed to be the ground truth. And then after we apply differentially private noise, then we end up with some kind of confidence interval. We added this noise, we protected the individual data, but we also have now created some statistical uncertainty. Much of the debate focuses on this. But in fact, these differential privacy, and here again are examples of research that focuses on that added noise, in a way is, I wouldn't say forgetting is perhaps too strong a term, but is overlooking the fact that much of the data sets we work on, including certainly census data, are not really ground truth. They are themselves affected by other noise, what we call data error. And of course, the Census Bureau knows that. In fact, we can even distinguish between quantifiable data errors particularly in US Census data, but the argument I'm making is really applicable to many other data sets as well, and unquantified, perhaps unquantifiable data error. The unquantified data errors are things such as misreporting. But there are other types of data errors that we can at least estimate, sampling errors, measurement errors. And as a matter of fact, Census has some estimates for what the kind of error is. And Census wouldn't know exactly by default what the exact ground truth is, but they have confidence intervals. They have estimates what is this error in their own statistics relative to the ground truth. So what we have to recognize is that rather than, as I was mentioning earlier, the reality of the ground being that there is a perfect ground truth statistics or data point here to which we add noise, we have to recognize that the reality is a little different. Because even before we apply differential privacy, the ground truth may be somewhere there in the confidence interval, and then once we add the differential privacy, then we are indeed extending, enlarging the amount of noise. But in essence, what we were really interested in tackling was to compare, in a way, the noise due to adding differential privacy to the noise due to the existing data error, in order to assess comparatively how bad is differential privacy compared to the noise already caused by data error. So in a nutshell, this is what we did. We focused on the US, one particular application of US Census data, Title I education funding. I'm going to discuss that in a second. And we simulated first the impact of data error, not differential privacy, but data error on funding allocation. And I will explain, of course, what I mean by simulating the impact of data error. And then we simulated the impact of differential privacy on funding allocations. And then we compare what we call misallocations. Misallocation are related to the theoretical ground truth, to the published estimates. And we compare the misallocations due to the data error alone, due to data error in differential privacy. And the key result is that we find out that misallocation due to differential privacy occur on the margin of, in our context, okay, we cannot necessarily generalize to other contexts, but in our context, they occur on the margin of much larger existing misallocation due to data errors, and you will see by how much in a few minutes. And I was hinting earlier that in the last few years there has been a convergence of computer scientists and economists, and indeed I was mentioning the name of John Abbott. There has been really great work, related work recently on Title I, which inspire our work as well. But differently from that work, we consider new context a full allocation formula for Title I, including most grant types, eligibility requirements, special provisions, official data from the fiscal year 2021, but importantly, we ask a slightly different research question. This privacy noise compared to existing data noise, and then we focus on the impact of Title I misallocations across different groups. Jingyu, please.
Yeah. Hi, Alex. It's great to see you again. Yeah, maybe you will explain later, but can you explain at a high level that how do you estimate the relative size of the data error and the error due to the different privacy? Because
definitely. I'm going to get to that.
Very limited knowledge about the true distribution.
Right. I'm going to get to that in a moment. A very important question, and please, probably in a couple of slides, I'm getting to this. Please, if it's not satisfactory, please feel free to bring up this question again. But in a nutshell, I can already give you the answer. In a nutshell, we cannot know what the ground truth is because the census itself cannot know the ground truth is, but the census does have estimates of the noise. They've been able over the years to calculate what the noise is, and therefore we use the information which the census itself publishes to create some different versions of possible realities where the ground truth of the actual data point changes every time. And this allows us to calculate then the potential possible misallocation due to data error. That is in a nutshell. And I'm going to get into more details shortly. Thank you. So yeah, let's get into the details. So as a background, again, the census data, as I was mentioning, is used for many important applications, is used by scholars, is used by researchers, but is also used by other branches of the US government to make significant funding decisions. One of the decisions, such funding decisions, is Title I education funding. More than 50 years ago, Congress established Title I education funding to support school districts in educating economically disadvantaged students. And funding is distributed to different school districts around the country using a rather complex formula that includes census data and estimates based on census data. In particular, the estimates focus on the number of children in poverty. And the way the Department of Education uses census data to allocate funds is public knowledge. It is described, it is complex, but it is fully described, and therefore we know precisely how it is done, and we can precisely replicate it. So we use the small area income and poverty estimates which come from census data. I will be referring to that in the rest of the presentation by the acronym SIPE. And this data, which estimates, is used to, among other things, to estimate the number of children in poverty in different districts, is then fed into this complex formula, which then produces the decisions and the allocation of Title I funding to different school districts in the United States. So we know precisely, we can replicate precisely how the statistics published by the US Census were then used by the Department of Education to actually allocate funding. So that's we start from that. But then, and this is the step, Jingyu, that you were asking me about, then we simulate uncertainty. we have to simulate, right? Because again, we know that, and census knows that the actual underlying published data, the actual mu I in a certain school district I, although it's presented as the ground truth, may not actually be the ground truth because it is affected by noise. And the census publishes some estimates about what the noise can be. Essentially, following prior work and Census Bureau guidance, we imagine an alternative estimate XI, where I is each school district in the United States, and we basically create this XI by using CI, which is the coefficient of variation for approximately normally distributed poverty estimates suggested by the census, as an upper bound on uncertainty in the poverty estimates. And CI is monotonically decreasing with total population. So essentially, we use the poverty estimates and the coefficient of variations that the US Census Bureau itself has produced to create these different possible poverty estimates. And then to that, we use a Laplace mechanisms to add to these data error estimates and produce then this xi tilde, which is in essence the sum of the data error and the differential privacy error. And this Laplace mechanism, so the Census Bureau has not yet announced any concrete plan for which specific differentially private mechanism they will use. SciPy itself currently does not inject noise for privacy and topography inputs. So what we do to illustrate how privacy deviations may affect these and similar products, and also to guide policymakers, we follow prior work and we use what is a rather standard Laplace mechanism, is commonly used in noise injection procedure, is provably differentially private. And what is important to remember is that the epsilon is a measure of how much an individual decision is a measure essentially of the risk of the re-identification. Determines essentially the magnitude of privacy deviations, where the lower the epsilon is, the stronger the privacy guarantees are, and typically, generally, that means more noise. Essentially, epsilon measures how much an individual decision to respond to census survey increases their own risk of unwanted disclosure. And by the way, we use pretty aggressive epsilon. So we use two different epsilon, 0.1 and 1. They are both pretty aggressive, considering the fact, by pretty aggressive, I mean that we are talking about loss of noise and also lots of, therefore, privacy protection. We do so because we essentially want to consider the worst case scenario in terms of data utility. Prior work on Title I suggested larger epsilons like 2.52, for instance. Larger epsilon means less noise, it means less privacy. So in essence, you can interpret the results I'm about to show you as results that are based on somewhat worst case scenarios for the loss of data utility, but also best case scenarios in terms of data protection. So what do we do finally? So the two steps, these were the crucial two steps, right? We simulate uncertainty by first simulating the data error and then adding the differentially private noise. And then we calculate, we measure misallocation. What is misallocation? Essentially,
can I ask a quick question?
Absolutely.
Yeah, just clarifying question. So XI here is the ratio of the poor students in school districts I.
The numbers in children poverty.
Oh, okay. And because I'm ignorant of this kind of methodology, so in which stage of this data cleaning, the Census Bureau apply this differential privacy?
Not yet. So not yet, right? The different they have not yet officially started producing and sharing publicly the differentially private transform data sets. But if and when they were to do it, they would not add this step. They would directly apply some kind of mechanism, which could be a Laplace mechanism, could be a different mechanism. They would apply directly to the original data, to what for them is ground truth. So this is an extra step that we add in order to try to simulate what is the impact of data error? Because again, census knows that there is error, knows what the distribution of error is, but census cannot, and no one cannot know what the exact ground truth is.
Thank you.
Thank you. While this is the key from the standpoint of our methodology, this instead is the key from the point of our calculations, the results. Because here we basically deviations in census poverty estimates can cause misallocations. How do we define misallocations? Misallocations are cases where the funding amount allocated to a school district differs from its entitlement in an imaginary noise-free world. Essentially, we take the published estimates of the funding YI based on the published number of published statistics by the census, such as what SAIPE, remember the acronym I used earlier, what SAIPE says is the number of children in poverty in the different districts that leads to official funding allocations the Department of Education has made for each school district I, and we compare against these ground truth, we compare instead our estimates, so what the Department of Education would have done had the estimate of the number of children in poverty been X tilde, where X tilde, once again, is the output of the combination of the differentially private transformation and the data error. And we repeat this process 1,000 times, and we consider then the possible misallocations that may arise from this process. When we average the misallocations, and misallocations are thusly defined across 1,000 trials, we found the following results. This entire bar from this point here to this point here is the total amount of dollars that the Department of Education has assigned to different school districts under Title I grants in 2021. And this total amount is $11.7 billion, okay? Due to data error alone, around $1 billion are lost in funding. And by lost, we refer to school districts receiving less than what they would have otherwise received in a noise-free, theoretical, imaginary noise-free world, the loss in funding that those districts suffer. So it's about $1 billion. What is the loss these districts could suffer due to the addition of differential privacy to this process? Well, with a aggressive epsilon at 0.1 epsilon, which, as I mentioned earlier, the smaller the epsilon, the more privacy, but also the more noise added. There are an additional $50 million lost by school district. Essentially, school districts are going to lose in terms of funding relative to this imaginary noise-free, error-free world, $50 million, with a slightly larger epsilon 1, which is still a good privacy level, just not as strong as 0.1, it's less than $1 million loss. And this, in a way, is in a nutshell, the key result we have, that the noise due to differential privacy and the negative impact it can have on school districts losing funding actually pales compared to the noise caused and the misallocation due to quantifiable data error. And from this, then we can engage in lots of interesting analysis. We can look at the heterogeneity of misallocation, because misallocation is not distributed equally across
Alessandro?
Yes.
Sorry, can I ask one question regarding the comparison you made?
Absolutely.
I think the data error, the loss from data error, if you like it, a lot of them come from the information technology not very well developed in the census data collection, right? So looking ahead, if we can think that data collection become more and more efficient and more accurate, in that sense, this blue bar will kind of shrinking over time. And if this blue bar is shrinking over time, then later on, maybe the loss from data error is comparable to the loss from differential privacy, right?
I think that's an interesting hypothesis, right? And I think it will be. I think it's a very interesting empirical question. That is a testable hypothesis, and certainly it would be interesting to measure over time how the blue bar and the orange bars evolved. There is a long way to go, right? Because that 1 billion is really far away from the 50 million and vice versa. And I believe that to some extent, the kind of data errors we're talking about here, some of them are almost systemic and inherent. Some of them could be reduced because, for instance, as we transition to other ways of collecting census data, rather than the approach that has been used for decades of sending with people going, census representatives going to houses and mail documents. There has been for now quite a while a discussion of transitioning to online census forms, etc. There are certainly interesting and exciting changes that are going to happen in the next few decades. The extent to which we can reduce that blue bar is still not known. I think it's a very interesting empirical question, and I think I look forward to see how that evolves over the next few decades, and whether indeed census data collected through electronic means. I'm pretty sure I will not bring the error to zero, but yeah, it may reduce it.
And also in your Samuel, and also in your next slide, if there's a rollout of this kind of information technology in data collection across different states, maybe like you can use that variation maybe to identify some of the changes over time.
I see your point, and I'm about to say something about that. So thank you so much, great points. Before I switch indeed to the next slide and I address your interesting follow-up points, did I hear correctly that there was another person who was about to ask a question? Did I hear that, or am I?
Maybe I can ask a quick question. So I just curious that, so this amount of the error from the DP, the differential privacy, is independent from the amount of error from ground truth error, or it also depends on some of the error of this ground truth error?
You mean the blue bar?
Yeah. So the error from the differential privacy, for example.
I see. Well, it's added to the misallocation due to data error. So it's in addition to.
But the two are kind of independent, right? I'm just curious.
My instinct is to say yes. I hesitate because I hope that I'm not saying something statistically inaccurate. By construction, yes, in that you apply, well, independent. Okay, let's clarify. You apply the Laplace mechanism on top of the theta error. So in the sense they cannot be independent because the Laplace mechanism is applied to an estimate of which is produced based on census distribution of error. So in the sense, it's not independent. But if you are asking whether it changes, whether there are other factors other than our data error estimates that would affect the Laplace mechanism, then my answer is no. And Ryan, if you're still connected right now, I don't see all the people are connected, and if you feel that this is slightly incorrect, feel free to step in. Okay. Okay. So let's see. I see we have about a minute. So let me hit a few key highlights here. I'll go a little faster. I'll focus just on a few key points, and then I look forward to. If we have time to discussion after 10 a.m. or 10 p.m. for you. So I was mentioning that the misallocations are not distributed, are not the same across the United States. And there are very good reasons why the misallocation are different across the school districts. Districts with fewer children in poverty have less dollars to use. The gains from all districts, there is a kind of zero-sum processors offset the losses for the larger districts. So you can see here the blue indicates districts which actually expect to gain for the application of these differentially private mechanisms. And in red, instead, you can see larger school districts which actually expect to lose. Essentially, gains decrease with population size and with poverty rate, which also means that the impact of applying differential privacy is not the same across different groups. It can be positive for certain groups. It can be negative for other groups, and in particular, other already marginalized community, as represented here on the x-axis. You see the positive values, so essentially positive misallocations, the groups that gain from the application of differentially private mechanisms, and on the left-hand side, the negative values, the groups such as, for instance, African American, which are going to lose. We also know we can use model smoothed misallocation by covariates with 95% confidence interval. Essentially, we can fit a generalized addictive model to the school district level combined misallocation using district population characteristics such as the population density, median household income, a proportion of different groups in the school district, etc., etc., etc. And this allows us to make other interesting discoveries because the positive values in this indicate districts that expect to benefit from combined data and privacy deviations. The negative values indicate districts that expect to lose. And you can see certain groups, for instance, groups with where district with the median income is less than $75,000, or the district with that are more dense in terms of population are those that actually are going to lose more than other districts. Finally, there are ways to try to counter for the noise and misallocation caused by differential privacy. We can essentially pay for differential privacy. We can pay for privacy. We can allocate the future regulation could allocate money to essentially pay for expected losses, specifically for the negative misallocation, so for the funding that certain districts are expected to lose. This amount it refers to expected losses. The amount grows if we instead consider the worst case scenario losses, because remember, we ran 1,000 repetitions of this process. So on average, across these 1,000 repetitions, this will be the expected loss. But in some cases, out of those 1,000 simulations, some of them had much larger losses. There are also some reforms which could be implemented in Title I, which would significantly reduce the loss, such as rather than using hold harmless, which is the current approach used by Title I, Department of Education following Title I funding, we could use moving averages, which can reduce misallocation and also decrease disparity. So, in a nutshell, and I hope that I have at least couple of minutes to go back then to the bigger picture. In a nutshell, what we found is that the misallocations due to differential privacy do exist. So there is no free lunch, going back to the economy discussion, but they exist on the margin of, in our context, much larger existing misallocations due to data error. Title I distributes the impact of this statistical uncertainty, be it due to data error or to differential privacy, unequally across demographic groups. However, there are a number of policy changes or just additional funding that can be provided to essentially decrease disparity, reduce or eliminate the losses that some school districts may incur due to differential privacy and still have privacy too. Essentially, conceivably, we could have the cake and eat it too, to some extent. However, caveats, we have focused only on the quantified data errors. We have used an hypothetical differentially private mechanism. As I mentioned earlier, we still do not know what specific mechanism the US Census will adopt, when and if it will adopt it. Laplace mechanism is a likely candidate, I believe, but we cannot know what will happen in the future. We did account for heterogeneity in user funds, and this was the focus of my presentation today. This was the narrow part of the study. I have 2 minutes left. I wanted to go back to my framing device. As I told you, I've been absolutely excited by what has been happening in the field of economics of privacy research in the last several years. But I also noticed how there has been somehow this contrast between either we get less regulation, less protection, more data, or we get regulation, more privacy. But if we get more privacy, we have to give away many of the benefits that we get from data. Much of my current research actually attempts to check whether, to the extent to which this is true, the extent to which this dichotomy between more data and more privacy is true, the extent to which when we lose privacy, we only lose autonomy, dignity, and freedom, which is already enough, or we actually bear economic cost, and the extent to which these economic benefits of data are allocated to different stakeholders. And in fact, the very last minute of my talk will be just a glimpse of a study I have recently completed with other colleagues at CMU, which tries to address the question of who really benefits from behavioral targeting, behavior advertising. Much of the research on behavior advertising has been focusing on the benefits that behavior advertising gives to everyone, essentially. This is a quote from an advertising executive who say behavior advertising is good for consumers because they see ads that they like. It's good for advertisers because they can allocate budget to consumers who are more interested in the product. It's good for publishers because publishers are going to sell more valuable real estate. Well, much of the research in our field is focused on the returns to investment to merchant advertisers of behavior advertising. Less research is less research is focused on publishers, and as surprising as this may sound, almost no research is focused on consumers, meaning that the benefits that consumers get from behavior advertising are more often posited than empirically demonstrated. Essentially, we typically, the discussion ends by pointing that behaviorally targeted ads are more likely to be clicked upon than non-behaviorally targeted ads. And this is taken as evidence that these ads are good for consumers. But the point that we make in our recent study is that the fact that consumers click on these ads more often than non-behaviorally targeted ads only tells us that these ads are reducing consumer search cost. But consumer search cost is only one part of the consumer utility function. We also want to know what is the price that consumers end up paying for the goods they buy through behaviorally targeted ads. What is the quality of the goods or the quality of the vendors that they would end up buying from when they click on behavior targeted ads. So essentially, we ran an experiment in which we compare vendor quality, product prices, as well as subjective self-reported metrics across 3 experimental conditions: the ads behaviorally targeted to consumers, the products that the consumers could find by searching, and just random products. And so we compare these 3-way how these may affect factors that are part of a consumer utility function. And essentially, we found that this is the key result: the behavior targeted ads are associated with higher prices and lower quality vendor than competing products that consumers can find in search, which means that at the very least, the impact of targeted display ads on consumer welfare is at the very least nuanced. And this is, to conclude, my goal of ending on a broader picture of what we are trying to do with our research. Essentially, what we're trying to do is to address these questions at the overlap of data, privacy, and economics. Thank you very much for your attention.
Oh yeah, thank you so much. And are there any further questions from the audience? Yeah, maybe I want to ask one very quick question about the result from these behavioral ads. So the reason the consumer is getting higher prices is because he's getting his matched product. So it's like because he's like willing to pay high, so the vendor charges the higher price. Is that because why the price of the product is higher?
So great question. So you're asking me what is our interpretation, the possible explanation for this price result, right? Did I understand correctly your question? Thank you. So while we don't have the tools through our experimental design to precisely or to conclusively address that question, we do have a hint of what may be happening. And let me, to show what the hint is, let me go back to the...
Also, when you talked about the experiment, it's like a lab experiment or...
Field experiment.
Field experiment, okay.
Yeah. Allow me just 1 second, please, because I'm trying to see where I can go back to sharing my screen. Okay, I believe that my screen is being shared again, okay?
Yes.
Okay, so the story we have, which we cannot demonstrate, right? But it seems a plausible interpretation. And interestingly enough, it's an interpretation which is based on a very well-known manuscript by Halverian. Is a very, very famous 1980 paper in AR titled "A Model of Sales." To explain, you see this part of the slide that I didn't mention earlier, because in the interest of time, I zoomed directly into this result, but I didn't say anything about this, right? So this is a very important result as well. I didn't think I had the time earlier to discuss it. What we find is that search results are heavily dominated by large vendors. So in our experiment, we see that when people search for certain products, essentially the first page of organic search results is dominated by companies like Amazon, eBay, Target, all companies in the United States. This experiment was done in the United States, or very large companies. If you look at the top 15 vendors by distribution in search results, there is no single small vendor. Okay, and why is that? Well, most likely because of the way the search algorithms work, the ranking algorithms. That the way, for instance, Google search algorithms work. They assign a quality score to vendors. Vendors that are more popular presumably get a higher quality score, and therefore the larger vendors dominate the search results. Which means in turn that if you are a small vendor, it is almost impossible for you to reach consumer through search results. You have to buy ads, and these ads could be search ads or could be indeed behaviorally targeted ads. So small vendors have faced this barrier to entry to appear in search. They have to resort to ads, and here is the kicker. If you look at Halverian model of sales from 1980, he suggested that if you have in a market informed and uninformed consumers, informed consumers are those that are informed about the different products sold by different sellers, and they are price conscious, and they will try to find the sellers that have the better price. And the uninformed consumers are those actually who don't invest time searching. They just buy from the first merchant they find, okay? That particular model was written in the 1980s, before the internet, so it was referring to physical searches. But we can absolutely extrapolate its implications to the internet world, and we can still consider that on the internet nowadays, there are indeed informed and uninformed consumers. The uninformed consumers are not going to engage in search. They're going to go to do comparison shopping. They're not going to spend much time in looking for the best product and the best price, etc. The informed consumers do. And this in turn implies, according to Halverian's model, that merchants will themselves self-select into two groups. The merchants who go for the informed consumers, which are the large majority of consumers, and therefore there is high price competition for those consumers, especially therefore in search. And the merchants instead who go for the smaller proportion of compared to the entire market of uninformed consumers. These uninformed consumers are fewer than the uninformed consumers, but to these uninformed consumers, merchants can charge higher prices. Though there is a smaller market share, but they can actually make more money out of them. And therefore, among these smaller merchants who end up going for the uninformed consumers and try to use ads to reach them, it is more likely to have higher prices, because they can try to take advantage, quote unquote, take advantage of these uninformed consumers. So this is a possible answer to your question. I cannot claim that we can conclusively demonstrate that this is the answer, but I found it quite fascinating that our results seem to be quite compatible with the work Hal did essentially 40 years ago.
Oh yeah, thank you. Yeah, maybe so if the speaker has more time, maybe I can try to receive one more question from the audience.
Absolutely.
Hi, Alessandro. Great research. Thank you for the presentation. So I have a question regarding about how we can generalize the research, and also whether some of the results can have some formal presentation. For example, is it possible to show that in certain kind of settings we can quantify the losses from the protecting the losses from the privacy, so that it's optimal for the social planner to use the Laplace error such that the social welfare is maximized?
Thank you for the question. Yes, I would say that this is one of the goals, right? One of the hopes, one of the objectives. That's precisely that's it. And but of course, also something that you mentioned at the very start of the question you asked is also very important. That we have to be careful about generalizing, right? Because in our scenario, we did find that the misallocations due to differentially private noise are really small compared to that of pre-existing data error. We cannot generalize that to other scenarios. So a social planner interested in using this type of approach in other scenarios should focus on replicating the approach step by step, rather than just jump into the conclusion that, okay, now we know for sure that differential privacy adds very small error to the pre-existing data error. That we cannot claim, that we cannot know.
Yeah.
Thank you.
Okay, yeah, I think time is already up, so I think maybe we have to wrap it up here. And I just want to say, so I think thank you very much to the speaker for the wonderful talk, and also thank you to the audience for staying out late, also sometime in the morning. So yeah, thank you again, Alessandro. Yeah, it was a really, really good presentation. Yeah.